Okay, so we are recording now, and right. So the next module that we are starting today is on bipartite matchings and edge colorings, and the topics we'll be covering from the text. These are 16.1, 16.2, and 17.1 up to 3 at least. Okay. And after that, we will come back to matchings, chapter 16, and we will cover non-bipartite matchings. Okay. Before we start with matchings, I'll just ask again because some students joined a bit later. Are there any questions or concerns pertaining to vertex colorings, the previous module that we finished before the break? Right, so we have done a bunch of things there. We saw the 5-color theorem. We proved the 5-color theorem, which is essentially the proof by Hewood. Then we proved Tate's theorem, which relates vertex colorings and face colorings, which are related by duality. It relates these to edge colorings in the case of cubic graphs, cubic planar graphs, right? So that is one of the birthplaces of edge colorings as a research area, and also matchings, because every color class in an edge coloring is a matching of the graph, right? So this is one of the birthplaces of matching theory, which is my own area of research. Matching theory was also it also started in some other forms from algebra and so on. Right, and after that we discussed coloring graphs that are not necessarily planar. And in particular, we observed that for any graph, delta plus 1 colors suffice. This is easy using the greedy heuristic. But then we proved Brooks' theorem, which says that actually the only graphs that require delta plus 1 colors are the complete graphs and odd cycles. I'm talking about simple connected graphs, right? For all other graphs, you need just delta colors, right? Okay, good. So that is all we have done in vertex colorings. Depending on how things go, there is a chance that we return to vertex colorings later in the course, but there is a high chance that the rest of the course will be consumed by matchings and edge colorings. Okay. So, okay, let's go to matchings. So just to remind you, a matching in a graph. Also, we can assume here that all graphs are loopless, is a set of pairwise non-adjacent edges. And since the graph is loopless, you might as well call them links, right? These are edges that are not loops. Okay. So just to give you an example, here is a graph that I will probably draw many times in the course because I like it, right? So this is not a bipartite graph, but right now we are discussing in general. Our focus will be on bipartite matchings, but I may use examples that are not necessarily bipartite. Okay, so here is a matching, right? There are two edges and they don't share any vertex. So it's a bunch of edges so that no two share a vertex. Okay, and you can see that this is not a matching of maximum size, because I can find a matching in this graph of size 3. And it's clear in this graph, you have 6 vertices. So any matching will have size at most 3, right? Okay, so so just some terminology before we get into the more interesting ideas. Right, so when we have a matching, let me just label these vertices 1, 2, 3, 4, 5, 6. Okay, and if you look at the green matching, then let's call the green matching M. Okay, and let's call the red matching N. So under the green matching, we can talk about vertices that are exposed and covered or saturated. I think I'll prefer saturated. Okay, so the vertices that are M saturated are those vertices that are matched. So M is the, oh, okay, sorry. Sure, I wanted to first discuss the red colored matching, my bad. So let's look at N. Okay, so this is the matching with edges 2, 3 and 4, 6, right? And so the N covered, oh, sorry, saturated. Maybe I'll use both terms interchangeably. Vertices are 2, 3, 4, and 6. And the other vertices, 1 and 5, are N exposed. Okay? Or sometimes I may say unmatched under N. Okay? And these are matched under N. So yeah, we'll be using a whole bunch of terms that mean the same thing. Right? And generally the term itself tells you what the meaning is. That's true for most things in graph theory. Okay, good. And if you look at the green matching, then notice that all of the vertices are M saturated, right? And likewise, none of them are M exposed. Okay, good. Great. So, okay, now if you look at the red matching, 2, 3, 4, 6, you can't add any more edges to this matching to keep it a matching, right? The only unmatched vertices are 1 and 5, and in this graph there is no edge joining 1 and 5. So we will say that N, while it is not a maximum matching, it is a maximal matching, right? So in this example, N is a maximal matching since we can not add any more edges to it to get a bigger matching, right? On the other hand, the green matching M is a maximum matching, which basically means that there is no matching in the graph bigger than M, right? Okay. So clearly one question you could ask is, what is the size of a maximum matching in a graph? And we have discussed various questions so far in this course about the size of various objects in a graph. Sorry, I've tangled my wire in my chair. My bad. Okay. Okay. So we are going to use alpha prime of G to denote the matching number of a graph G. Okay. Am I visible? Okay. So that's the matching number of a graph, and that is defined as the size of a maximum matching in G, right? And so in our example, alpha prime G is equal to 3. Okay. There is yet one more definition I want to cover, which is what is a perfect matching. So matching is perfect if a matching M is perfect if there are no M exposed vertices. Or in other words, every vertex is matched with some other vertex under the matching M. Right? So in our example, G here, M is not only a maximum matching, it is in fact a perfect matching. So, right, so in our example, M is a perfect matching. I generally won't write down perfect matching. I'll just abbreviate it to P dot M dot. Okay. Clearly, if you have a perfect matching in a graph, that is a maximum matching, right? You've matched all the vertices, so there can't be any matching bigger than that. However, a maximum matching need not be perfect, right? So just to give you an example, first of all, it should be clear that in a graph that has a perfect matching, you're going to have an even number of vertices. So I could take any graph with an odd number of vertices, and now I will have a maximum matching, and clearly that will not be perfect, right? So a perfect matching is clearly maximum and requires the graph to have an even number of vertices, right? You might ask, well, does that mean that every graph with an even number of vertices has a perfect matching? And the answer is easy to see that it's no. You have a graph with an even number of vertices and it has no perfect matching, right? And the maximum matching is size 1 here. Okay, good. So, well, one question that arises is, can you compute the matching number of a graph? Now, this is not a course on algorithms, but I'll say a few things here and there without getting into algorithmic details. So the answer before you even ask the question is yes. Turns out that unlike unlike the stability number or the clique number or the chromatic number of a graph, the matching number of a graph is actually computable in polynomial time, or if you don't care about that, it's efficiently computable. Okay, so how many of you have seen in previous courses that alpha prime G is computable in polynomial time? Anand, yes. Anyone else? Okay. So yeah, so it is computable. And before I go ahead with matchings and more theoretical discussion, I just want to point out that matchings have a lot of applications out there, especially bipartite matchings, because a lot of real world problems boil down to bipartite matchings. And I'm not exaggerating here. In fact, you can look up one of the prizes in one of the Nobel Prizes in economics had to do with matchings as well, because they use matchings to facilitate organ donation in the UK, and that led to a Nobel Prize in economics. This is maybe in the last 10 years or so. And apart from that, there is a whole lot of applications of matchings in the industry, starting from optimization and also in very theoretical fields like theoretical physics and organic chemistry. Okay, but again, this course is not about applications, so we will not really be talking about them. You can read about them on the internet in many places. Okay, so in the case of matchings and in other topics in graph theory, but matchings is really a prime example, there is a great distinction between bipartite and non-bipartite case, in the sense that bipartite matchings turn out to be a lot easier. They are not trivial by any means, they're still non-trivial, but they turn out to be a lot easier than matchings in general graphs, I mean non-bipartite graphs, right? So that is one of the key reasons why in any text on matchings, you will generally see a separation between bipartite matchings and non-bipartite matchings. Also, once you understand bipartite matchings, it really helps in understanding the more technical details that are required in non-bipartite matchings, right? So with the same spirit in mind, we will first study bipartite matchings, and then we will move on to general matchings in the next module. Okay? But before we go there, let's ask some more basic questions about matchings. So while the course is not algorithmically focused, some algorithmic questions are going to help us in understanding the graph theoretic ideas and unraveling them. Okay, so one question you could ask is, if you're given a matching M in a graph G, under what circumstances can you find a bigger matching? Okay, so supposing I give you some matching and I ask you to find a bigger matching. Okay, let's start with an example. I'll take the same example again. Yeah, it was red. Okay, so let me take this as my matching M now. Okay, so this was what previously was N, I believe, but now I've switched it to M. Doesn't matter. Okay, so you have this matching M with two edges. Well, actually, let's start with a smaller matching. Let's start with this guy, just one edge, right? Okay, so now you can find a bigger matching by adding this edge. And that's because your matching, it was not a maximal matching, right? So clearly one answer is, if the matching is not maximal, if M is not maximal, then there exists an edge UV in the graph that is not in the matching, such that both U and V are M exposed, right? So just to look at this example, our graph was the one given, and our matching was just a single edge. And in this case, we can see an edge UV, that is not in the matching M, and both the vertices are M exposed. So then I can add this to my matching and get a bigger matching, right? So that is clear. Okay, so if there's a single edge whose both ends are M exposed, then you can just add this edge to the matching and get a bigger one. So what if your matching is maximal? So maybe the more interesting question is you have a maximal matching. Okay. So now how would you find a bigger matching? Under what circumstances can you find a bigger matching in the graph? So what am I looking for? I'm looking for some kind of structure in the graph. If there is this kind of structure in the graph, then maybe I can find a bigger matching in my graph. Okay. Any guesses? Maybe you have seen this before, so you can answer based on your previous knowledge. So what structure in the graph could help me an augmenting path? Right. Okay. So Anand is saying that what we want is maybe a path like this. Supposing there is a path in the graph that looks like this. So this is a matching edge, this is a matching edge, and these vertices U and V are both M exposed. Okay. In this case, Anand is saying that the graph has a bigger matching. Can someone apart from Anand tell me how I would get a bigger matching?
Substitute red vertices such that U starts from U and alternates.
Exactly. So instead of the two edges that are in the matching on this path, I will take the other three edges. Is that what you're saying?
Yes, sir.
Right. Exactly. Right. And the rest of the matching. So remember, this path is not the whole graph. The graph can have other red colored and not red colored edges. But on this path, I can switch the matching edges and the non-matching edges, and that will give me a bigger matching, right? And it will be a matching because the two ends of the path were M exposed, and so I could very well cover them with the matching, right? So this is what is called an M-augmenting path. I'll write down the formal definition, but this is an example of an M-augmenting path. And can we, in this graph, find an M-augmenting path? Can someone tell me, can someone show me an M-augmenting path in this particular graph? Okay, so I'm going to go with, so there is 1, 3, so there are two answers. Let's discuss both of them. So the first answer is 1, 3, 6, 5. 1, 2, 3 to 6 to 5. Is this an M augmenting path? Well, 1 is M exposed, 5 is M exposed. The problem is that 3, 6 is not a matching edge. This is not in the matching, right? So Shivam corrected himself and said that this is not an M augmenting path. So now let's look at the next one. There's a bunch of answers. I'll go with the first one, 5, 2, 3, 6, 4, 1. 5, 2, 3, 6, 4, 1. And that is indeed an M augmenting path. You can see that the alternate edges 2, 3 and 6, 4, they are in the matching, and the last two vertices 5 and 1 are M exposed. So we could very well switch these red edges by the green edges on the path, those which are not red. Okay, and this gives us a matching of size 3, which is bigger than the original one, right? Okay. So what is clear is that if there is an M-augmenting path, then you can always find a bigger matching, right? So if there exists an M-augmenting path P. So I want you to view matching as a set of edges. Well, matching is a set of edges. I also want you to view a path as a set of edges rather than a set of vertices or a sequence of vertices. Okay. So if you view the path as a set of edges, then what you are doing is that you are constructing a new matching M prime by taking the symmetric difference of the original matching and this path. Okay. And this gives you is another matching, and in this case the cardinality of M prime is exactly equal to the cardinality of M plus 1. Okay, you will increase the size of the matching by 1, and so you'll get a bigger matching. So if there exists an augmenting path, then in particular M is not a maximum matching. Okay, clearly the question now arises, is the converse true? So if the matching is not maximum, then does it mean that there exists an augmenting path? And Shayoni here says, yes, that is true. So yes, it is indeed true. And we will write a small proof of it very soon. You can try it yourself, but maybe we'll get to it today itself. So the answer to jump ahead is yes. And we will prove it shortly. Okay. Before that, I want to write down the formal definition and also define something else. So right. So let's define an M-augmenting path formally, and on the way we will also define some other terms which will be useful to us. So what is an M-alternating path? I won't write down the formal definition, right? So G is a graph, M is a matching. So M-alternating path is any path whose edges alternate between being in M and not being in M. So it could be a path of any length, odd or even, doesn't matter. What is true is that the alternate edges are in the matching and not in the matching. So this could be an example. So the alternating path could either start and end with M edges, or start or end with edges that are not in M. Okay, so it's any path so M is the red colored matching, whose edges alternate between being in M and not being in M. Okay, I hope that's clear what I mean by that. Okay, good. And now an M augmenting path is nothing but an M alternating path whose two ends are M exposed. So in this case, the path will have to start and end with non-M edges. Okay. An M augmenting path, or let me call it a UV path, where U and V are the ends of the path, is an M alternating path so that such that U and V are both M exposed. Okay, so this looks like this. You have a path which is M alternating, but the last two vertices U and V have to be M exposed. So this means that these edges are not in M. So then this has to be in M, this has to be in M, and your path could end here, right? And U and V, this edge is also not in M. Not only is it important to say that they are not in M, it's actually important to say that these two vertices are M exposed, right? Good. All right. We will also need the concept of M alternating cycles. Okay, so let's just see what a cycle looks like. Well, can it be an odd cycle? In an odd cycle, it's not possible, right? You have an M edge, then you have an M edge, and now this edge needs to be in M, but it can't be in M because then it won't be a matching. So M alternating cycles are necessarily even length cycles, and then it's the same concept, right? So an M alternating cycle looks like this. Okay, so it's the same definition. So maybe I'll just put it here. M alternating path or cycle is any path or cycle, right? And in the case of cycle, it's clear that it has to be even length. Right? Whereas an M alternating path could be odd, even, doesn't matter. Okay? Good. Are there any questions or concerns regarding these definitions? Okay. So, what we will actually prove now is that whenever a matching is not maximum, it is precisely because there is some M alternating path in the graph. Right. So this is theorem 16.3 proved by Berge in 1957. A matching M in a graph G is a maximum matching if and only if G has no M-augmenting path. Right? What we have already observed, if there is an M-augmenting path, then it is not a maximum matching. Okay? So we have proved the forward direction. We have proved the contrapositive of it, which is the same, right? And now we need to prove the reverse. Which is to show that if there is no M-augmenting path, then the matching is indeed maximum. So we'll again prove the contrapositive. We will say that supposing we have a matching that is not maximum, then we need to show the existence of an M-augmenting path. Let M be a matching in G that is not maximum. Then our goal is to argue, or well, to show the existence of an M-augmenting path. Okay. um just a small algorithmic comment. So yeah, in matchings I think I'm going to make a few more algorithmic comments because it's one of the topics that is covered extensively in any algorithmic course, whether it's offered by the CS department or the math department. You will see matchings in many of the algorithmic courses, right? um, so the one comment I want to make at this point is essentially any algorithm that finds a maximum matching, whether it's in bipartite graphs or in non-bipartite graphs, the main crux is to find M-augmenting paths, right? So if you can keep finding M-augmenting paths, then you will be able to construct bigger matching. And at the point you cannot find an M-augmenting path, this algorithm will give you some kind of certificate that an M-augmenting path does not exist, and so the matching you have is maximum, right? Okay. But anyways, that's just a small comment I wanted to make. So we want to prove this, but before we prove this, I want to take a small aside, which will be used in the proof of this result. Okay, and that is there are two ways to think about it. Either you can think about union, or you can think about symmetric difference. So depending on how you think about it, you will get different answers, but they are both convenient ways of thinking about the concept of two matchings. I personally find union a bit easier to discuss. So let's take the union approach. Okay. Supposing I have a graph G, and I give you two matchings, the red matching and the blue matching, right? So let's use colors. M is a red matching, and N is the blue matching. And these ideas that we're about to discuss, they're going to be extremely useful in most of the remaining course. Matchings, edge colorings, you will find these, the union of two matchings to be a very useful concept in understanding these topics. So that's why I want to spend some time on it, even if that means that we can't prove theorem 16.3 today. Okay. So I want to think about what would the graph where you keep all the vertices, it doesn't matter. What we are really interested in this module is the edges of the graph. So what does the graph look like if you just keep the red and the blue colored edges and you throw away all the other edges in the graph? And chances are that you have seen this discussion in your previous courses, even maybe in MA 2130. So what does it look like if you just look at the graph with the red colored edges and the blue colored edges? Anyone? Vertex disjoint set of alternating paths and alternating cycles. Yes, that is right. So, right. So let's think about it. So if you look at any vertex, so it's one way to think about it is just look at one vertex, V. Okay. Well, there are a few possibilities. Either this vertex V is not matched by the red or the blue edges, or it is matched by one of them, and not the other, or it is matched by both of them. Okay, so one possibility is it looks like this, or it looks like a vertex with a red colored edge. Okay, or it looks like a vertex with a blue colored edge, which I will not draw. It looks the same as the before. And now let's look at the next possibility, which is that it is um, M covered and also N covered. So then you have a red blue colored edge and you also have a red colored edge. Something like this. We are missing one possibility, which is that the red edge is the same as the blue edge. Right? There is nothing stopping from that happening. So it could be that the red colored edge is the same as the blue colored edge. Okay? And now if you think about the whole graph, well, every vertex has degree 0, 1, or 2. Okay? So that means that the graph induced by the red and blue edges, or formed by the red and blue edges, will look like a bunch of paths and components, because the only connected graphs with all vertices having degree 1 or 2 are paths and cycles. Right? So each component of the graph G induced by the red colored edges and the blue colored edges is either a path or a cycle. And a path includes K2, right? So you could also have K2s. And in this case, you will have either it could just be a red colored edge or just a blue colored edge, or it could be this case where it's the same edge that is colored red as well as blue, right? So all the components of the graph are going to look like this if the graph induced by the red and blue edges, right? So let's just draw some examples. You could have components like this. The vertex colors don't mean anything. It's just because I'm lazy to draw black colored vertices, right? So you could have paths like this, or you could have a cycle that looks like this, right? And these can be called M alternating. There are no odd cycles. Exactly. There will be no odd cycles. All the cycles will be red, blue alternating, and that implies that they'll be even. Thanks. Right. So actually, let's just put that here. Is either a path or an even cycle. Okay. Great. And these can be viewed as M alternating paths or N alternating paths or cycles, but you could also call them MN alternating paths and cycles. Okay, so I won't write down the formal definition. You get the idea. They are all paths are MN alternating paths, all paths and cycles or cycles, with the exception of K2s that look like they are colored red as well as blue, right? So there could be these components and these are not MN alternating, right? There is a single edge and it belongs to both M and to N. So in particular, if you take the symmetric difference instead of the union, these K2s will be thrown away, right? And what will remain will just be MN alternating paths and MN alternating cycles. So yeah, so in the symmetric difference, you will have only Mn alternating paths and cycles. But if you take the union, then you will also get these K2s that are red as well as blue in color. Okay. Are there any questions or concerns regarding these observations? I mean, I didn't write down formal proofs. These are easy observations. Essentially, it's all MA2130 material. Okay, good. So this way of visualizing um, the union or the symmetric difference of two matchings turns out to be extremely useful in studying matchings and also in edge colorings. Okay, good. Um, so with that in mind, actually, you know what? I'm going to leave this theorem's proof as a exercise to you. I'll give you one hint, and I'll leave the rest of the proof to you as an exercise. So we are trying to prove this result. M is a matching that is not maximum. That means that there is another matching that is bigger than M. This implies there exists a matching N such that N has more edges than M. Now, what you do is you consider the symmetric difference or the union of M and N. And now you argue that in this symmetric difference, you will find an M-augmenting path. Argue that there exists an M-augmenting path in the graph if you look at the symmetric difference of M and N. Okay, and the rest of it is do it yourself. Okay, so this argument is do it yourself. Okay, and that's the end of the proof. Are there any questions or concerns? All right. If not, then notice that this theorem 16.3 has nothing to do with bipartite graphs. It's about all graphs. Great. It's actually an easy result, as you will see when you go through the details. Okay. It just requires this idea of looking at two matchings and taking their union or symmetric difference. Okay. And tomorrow we will start with bipartite matchings, and we will look at we will discuss Hall's theorem and probably also prove it tomorrow itself, which basically gives you necessary and sufficient conditions for a bipartite graph to have a perfect matching. We will see a slightly more general viewpoint, but one of the consequences is that it tells you exactly when does a bipartite graph have a perfect matching. And in fact, the proofs we'll be studying will be more or less algorithmic. I won't spend the time to make them algorithmic. If you are interested, you can try to do it yourself. Okay. All right. So yeah, if there are any questions or concerns, please go ahead. We are already past the time, so I'll be here for another 5 minutes or so. Oh, by the way, sorry. Tomorrow there is no lecture because tomorrow there is an election. I checked with the head of the department and I was told that we can't have a lecture tomorrow. So the next lecture is actually on Thursday, which I believe is 8th of April. Okay. And that is when we will continue our discussion on bipartite matchings. I'll put an announcement on Piazza regarding there being no lecture tomorrow. So I'll turn off the recording.